my name is Diana Ivy Cedeno, and today I'll be doing my video lecture on ventilation. So these are the learning objectives. Describe why ventilation is not evenly distributed through the lung. Describe dead space. Describes the factors that affect alveolar ventilation, and you want to calculate ventilation, dead space, and the VD/VT ratio. So distribution of ventilation. In a healthy lung, ventilation, which is V, and perfusion, which is Q, are not even. In a normal healthy lung, the VQ ratio is 0.8, and it is best matched at the bases of the lungs because gravity will pull more blood towards the bases of the lungs rather than the top, which is the apices. And this explains it too. The alveolar in the apices, so this top part of your lungs, are larger, so they're harder to ventilate because once you breathe gas in, the gravity will automatically just push it down to the base of your lungs. And ventilation is described as gas moving in and out, so the way you're breathing, and then perfusion is blood supply. So a few factors that affect the distribution of ventilation. The first one is the shape and height of the lungs. So the shape and height which causes thoracic expansion. So at the apices you don't have much room to expand, so that's why the alveoli are much bigger, and then at the bases the alveoli are much smaller. So when you breathe, the bottom or towards like your stomach, the bases of your lungs expand more, and you can tell when you breathe and you don't feel anything really moving at the top. It's mainly just at the bases of your lungs because that's where all the air is going to be pulled towards. And then transpulmonary pressure gradients are the same, so it's just like how thoracic expansion. The pressure gradients also affect the distribution of ventilation. So at the top part of your apices, it's at negative 10 centimeters of water, which that's a lot of resting volume in there, and then at the bases it's negative 2.5 centimeters of water of resting volume. So you can think of it as your lungs as a glass of water. So if you have a lot of water, that means that you can't really add more water to that cup, so that will be like your apices part. But if you don't have a lot of water in your cup, if you just have 2 centimeters of water in your cup, that means you can add more water in there. So that represents the base of your lungs. So the water is kind of the gas that flows in it. So if you breathe a lot in, it's going to go straight down to the bases, and it's not really going to go up towards your apices. And then in smaller airways, each respiratory unit vary in the compliance and the resistance of your lungs. So next I'll be talking about dead space. In healthy lungs, we do waste some gas due to dead space, and this is because if you don't have dead space, that means your lungs are completely clear. There's nothing left over, and that could cause your lungs to collapse. You always want to have some extra gas in there so your lungs don't just fully just recoil and then they can collapse. So the first kind of dead space we'll be talking about is anatomic dead space, and this is gas left in the conducting airways. So that's mainly like in your trachea, like before it branches out to the bronchioles or the alveoli. And the anatomic dead space, it doesn't go all the way down to your alveoli during respiration and then during inspiration. And then during exhalation, there's a little gas left over, and that's what I mean by there's always gas left over, so that way your lungs don't collapse. And then it stays in there, and then you just breathe it back in, and then that extra air that's staying in there, that's when it goes straight to the alveoli. And then the next dead space is the alveolar dead space, which is volume of gas ventilating unperfused alveoli. And so that means that it's the gas that's left in the alveoli that doesn't have the perfusion, so it means that there's no blood flow. And with this, you don't want to see a lot of alveolar dead space because that could mean that you're not getting any blood flow at all, so it could be an indication for a pulmonary embolism. And then physiological dead space would just be the sum of the anatomic dead space and the alveolar dead space. And this is normally 1 milliliter per pound of your ideal body weight. And a normal, if you don't know, a normal is around 150 milliliters. And then if you have a patient that has their weight in kilograms, it would just be 2.2 milliliters per kilogram. And then physiological dead space doesn't participate in gas exchange because it's just getting rebreathed. So like I said, you don't want your lungs to completely just have no gas at all because that could make your lungs collapse. So you always just want to have at least a little bit of the physiological dead space that doesn't participate in the gas exchange. And then the more dead space you have, the less efficient your tidal volume is. That eliminates the CO2. So if you have a lot that's just left over, you're not getting rid of the CO2 that you need to. So that means that your body's still retaining all that CO2, and that could be potentially really bad. So here's just a picture. So here's the conducting airways where you would have the anatomic one, or the anatomic dead space. And then here in the alveoli, you would have the alveolar dead space. And then this just shows that both of these, the anatomic and would just be the alveolar equals the physiological dead space, which is the non-perfused alveoli. So with ventilation is expressed in liters per minute of fresh gas that enters the lungs. And you always want to make sure your alveolar ventilation is less than your minute ventilation, which is caused to dead space. So your minute ventilation is your total volume moved in and out per minute. So it's just how you're breathing right now. It's just how much volume goes in and out of your lungs. And this is expressed in VE equals, which is minute ventilation, times frequency of breathing, which is the same thing as your respiratory rate, times tidal volume, which is the amount of air that is going into your lungs. And this is all driven by the carbon dioxide production. And for a normal minute ventilation, it would be roughly 500 milliliters. So now your alveolar ventilation, it is the amount of fresh gas that reaches to your alveoli per minute. So when you breathe in, it measures how much is actually going all the way down to your alveoli and what is getting ventilated. And that is expressed in VA, which is alveolar ventilation, equals VT, which is tidal volume, minus the dead space, and then it would be just times the frequency of breathing, which is your respiratory rate. And then when you want to calculate the VT-VD ratio, this counts a more accurate assessment of alveolar ventilation, and it indicates how much ventilation is lost to dead space. And this would be the equation. So the VD ratio is PCA2 minus PeCO2 divided by PaCO2. So this is arterial carbon dioxide, and this is exhaled carbon dioxide. And this could be represented, this ratio could be represented in a percentage, or it could also be represented in a decimal. And the VT ratio needs to be in a kind of lower number, just so you know that gas exchange is actually happening. If it's higher, that means that you're not having good gas exchange. And also, if the PaCO2 equals the PeCO2, that means that there's no dead space happening. That means you're losing all that dead space. And then the PeCO2 must be less than the PaCO2, so the exhaled carbon dioxide must be less than the arterial carbon dioxide due to the anatomical and alveolar dead space. And it is less because So the exhaled is less because since there's leftover air that stays in the conducting airways, that means that the amount of carbon dioxide that you're exhaling would be less than what you're getting in your ABG, so your arterial carbon dioxide, because your arterial is the amount of blood that's the amount of CO2 that's in your blood versus the amount of CO2 that's actually in your lungs. So the normal range would be 30% or 0.3, or the normal amount, and then the range could be anywhere from 0.2 to 0.4, which would be 20 to 40%. So the efficiency of ventilation, you should have a low oxygen cost of breathing, and you should also have a low production of CO2. And you can assess this by having to do ABGs, which is the arterial blood gases, which will assess how much carbon dioxide is in your arteries. And the effectiveness of ventilation, it's most effective when the removal of CO2 is, or it's the same to maintain a normal pH. And a normal pH is 7.35 to 7.45. And you would calculate the effectiveness by PCO2 equals VCO2 over alveolar dead space. And a normal resting CO2 production would be 200 milliliters per minute. So any complications with ventilation is that if you have any lung diseases, it could cause a low alveolar ventilation. And then if you have high do it like this. So if you have high respiratory rate, which means that you're just breathing a lot, and you have a low tidal volume, which means you have rapid shallow breathing. This could mean that your alveoli isn't getting perfused. So if you have rapid and shallow breathing, that means that you're just breathing in and out really, really fast and nothing is getting really pushed down to the alveoli to get perfused. And this could cause hyperventilation. So hyperventilation would be if your arterial carbon dioxide is less than 35 millimeters of mercury, and that means that you would have a high range of pH, which should cause respiratory alkalosis. And then if you have hypoventilation, that means that your arterial carbon dioxide is more than 45 millimeters of mercury, and which could make you have a low pH, which causes respiratory acidosis, meaning that you just have a lot of carbon dioxide. So I have a few questions for you. So if your frequency of breathing or your respiratory rate is 15 breaths, and then your your tidal volume is 450 milliliters, and the patient has normal dead space, I just want you to calculate the minute ventilation and the alveolar ventilation. And so those answers for minute ventilation, it would be 6.75 liters per minute, and this would be because since the equation for minute ventilation is the frequency of breathing times the tidal volume, and that would equal the 6.75 liters per minute, because you would have to convert that into liters instead of milliliters. And then to calculate the alveolar ventilation, what you would do is It is the tidal volume minus dead space, and this patient has normal dead space, and it would be, and then you would divide that. You would divide the tidal volume minus the dead space, and then once you get that, you would times it by the frequency of breaths, and so that would be 450 minus 150, because normal dead space is 150 times 15, and you would also have to convert those from milliliters into liters, so the answer would be 4.5 liters per minute. And then my next question is to calculate the VD-VT ratio. And the PaCO2 is 40 and the PeCO2 is 20. And the answer for that would be 0.3, which is the normal value. So how you would calculate that, it would be PaCO2 minus PeCO2 divided by PaCO2. So 40 minus 28, which is 12, divided by 40 equals 0.3, or 30%. And then my last question is, which factors affect the distribution of ventilation? Select all that apply. A, shape and height of lungs. B, transpulmonary gradient. C, even VQ ratio. D, apices have less ventilation. And E, bases have more ventilation. And the answer of that
May I have your attention, please? The lobby closing in 15 minutes at 2 o'clock.
It would be A, B, D, and E. And we know that this should be switched. The VQ ratio is never even. It's the normal range should be 0.8.
So where the photocopiers and printers will shut down in 5 minutes at 1:50.
And then I just have a video that you guys can watch that explains more about dead space and this.
They can have a good weekend.
And then this is just my references. Thank you.